Thanks very much, Bob. Susan opened the session, today's session, with a call for managing big data, and she referred to genetics, genomics and phenotypic data. The groups that I work with are trying to dream of managing even bigger data sets, where we take that biological information and juxtapose it with agroecological information, and then bring to bear as best we can economic evidence about the likely consequences of targeting one's ever scarcer research dollars to address particular problems on particular crops in particular locations, and thinking about the relationship between those on-farm technology performance and the market consequences of that. The work I'm going to do today is in the sort of spirit of that assessment. What we started, our point of departure for this work was some work we published last year in an attempt to get our empirical handle around what's the global extent of stem rust, as best we could estimate it, and what the economic payoffs may be from redressing the prospects of a UG99 spread around the world. So we worked with folks at CSIRO and the USDA Cereals Disease Lab, University of Sydney, CIMMIT, and many other folks, to come up with a modelled view of the likely climate suitability, that's the areas in blue there, vis-a-vis the areas where stem rust may persist interseasonally, and to do this all in a georeferenced framework, so that we could then juxtapose that information against data we'd prepared on where in the world is wheat produced. And so here is an example of the map that we published last year, and then went beyond that to do a probabilistic assessment of what the likely yield loss consequences would be on average from year to year if we had removed, in a sense, we talk in counterfactuals, so if we had removed the resistance that we see to stem rust over the last 50 years, which is in the process of playing its hand out at the moment, what the likely consequences would be for an on-average production loss. So our estimates were that there was about, on average, about 6.2 million metric tonnes of wheat that could be lost, and attributing that loss to the spread of stem rust. And then we asked the even harder question that given that loss over a period of time, what's the likely justified research investment that one could argue for? We all call for more R&D funding, but can we put some hard economics around it? And we came up with an estimate there was just over $50 million that could be invested to alleviate the consequences of stem rust globally that was economically justified, and that's $50+ million year in and year out. It's not a one-shot investment in R&D spending, it's an in perpetuity investment. So that gives rise to obviously the same suite of questions with respect to stripe rust. And that was the challenge Hans gave us to work with folks in the BGRI program to look at what is the global extent of this disease, where is it likely to occur and persist, what's the area of and production of wheat that would be susceptible to this disease, what's the likely global consequences of a loss that could be attributed to this disease, and what are the economic implications of that. So we started the exercise with an event at the Delhi meeting of BGRI, where that kicked off a survey that we did of you folks to get at least a collective sense from you as to the extent of stem rust, stripe rust, I should say, around the world. And so here's a snapshot of the sort of geographical feedback we got from you, where we characterised the occurrence of stripe rust is rare, localised in some seasons, localised in most seasons, widespread in some seasons, and widespread in most seasons. And you can see a fairly clear demarcation between the pre and the post-2000 period there, where the sort of geographical extent of this disease, at least from the reconnaissance from the field that we're getting, which reinforces what we see in the literature, that there is something happening with this disease, that the current situation or the future is something different than it was in the past. We also asked respondents to give their perception of what might be causing this change in the spatial footprint of the disease. So we had 15 of the 29 respondents suggested a increase in the aggressiveness, the sporulation of striped rust is one of the explanators. Folks who flagged that as an issue also flagged a changing climate footprint, extent of the susceptible wheat, pathogen adaptation to slightly warmer climate regimes and so forth. So there's not a consensus, I should say, from this survey as to what folks are thinking is causing this, but nonetheless the evidence suggests that there is a move afoot. Just to show you, using data from the USDA Cereals Disease Lab over time, what the nature of the footprint of striped rust is in the US. The CDL folks, as you probably know, have been putting together loss data attributable to rusts for quite some time. And so maybe if we just kick off this graphic here, and you can see, if you track the time over the last 50 years, that in these data, something different's happening too. Fair concentration up in the Pacific Northwest and California up until the mid to late 1990s. And then after that, a movement of losses attributed to this disease further eastward across the US. One of the things you can see in this, that there's a high degree of stochasticity to where in the US these losses occur. And that's one of the things that we took into account as we move forward in our evaluation exercise. The first thing to think about is, like we did for stem rust, where in the world this disease is likely to persist and occur. And this is modelling work that's still a beta version. We're just in the process of fine-tuning this map, and soon we'll put it out for some peer review. So if any of you have got some feedback based on looking at this map, I'd like to hear it. But essentially, we're modelling the climate suitability of this disease, knowing something about the phenology and pulling through expert wisdom and published scientific evidence about the sort of temperature moisture regimes that set the growth thresholds for this particular disease, based on the premise that we actually have a plant host that's ubiquitous around the world. So we're just modelling the climate suitability of the disease per se, which makes this quite different from statistical exercises where we look for the occurrence of the disease and then get correlates between climate and so forth and try and then project spatially where the disease might occur. The problem with those approaches is that they confound the environmental conditions that are appropriate for the host with the environmental conditions that are appropriate for the disease, and what we've tried to do is separate those two. So we get a sort of modelled view of the persistence and seasonal suitability of this disease worldwide, and overlaid that on our footprint of a measured footprint of where in the world wheat production takes place. So our preliminary estimates suggest that according to area share worldwide, about half of the world's wheat crop is actually climate suitable for the growth of this disease. That doesn't obviously mean the crop gets hit every year, year in and year out. As you saw from the US experience, it's quite a stochastic process from year to year. And then about just under a fifth of this area will the disease persist from season to season. And this relationship between the source and the sink has really substantial implications in terms of the risk exposure that farmers have if, as in some locations, the persistence of the disease is spatially distinct from areas that are subject to infection from the disease. That puts a whole different sort of risk profile on farmers if there's a much tighter spatial concordance between where the disease persists from season to season and the consequences of the disease over time. If you read the literature, so knowing or having a view about where in the world this disease is likely to occur is a good start, but that's a long way from coming up with any estimates of what the likely production or yield consequences of the disease are and what the economic implications of that are. And if you read a lot of the literature, there's lots of reviews about stripe rust and stem rust and so forth, where folks will go and pick anecdotal evidence about the losses attributed to these diseases. And I call it a point maximal approach, that they'll often find a location or a locale or a particular year or series of years where there's a very substantial loss and are suggestive that that's the nature of the losses one might experience in a much more expansive spatial footprint or intertemporally. And that's subject to all sorts of pitfalls, as you might imagine. Not least here, if we look at stem rust, for example, this is the USDA CDL's data on the percent loss of the national wheat crop over nearly 100 years of data. And you can see there's these episodes of really substantial losses. And if I just pointed to those as being emblematic of the types of losses one might expect from this disease, one would be grossly overstating the likely losses over a period of time that would be attributed to this disease. So no doubt these losses are severe for particular locations in particular years, but it's not a good representation of the overall loss that's attributable to this disease at the national level, let alone at a global level. So for example, in 1935, when there was about 24% loss of the entire US wheat crop attributed to stem rust, in that year, if I remember right, Minnesota's loss was 60%. So if I took Minnesota's loss as emblematic of the US, I would be grossly overstating the losses that occurred in the US, and that same principle applies when you try and expand data like this for the US and apply it to the rest of the world. And you can see this big intertemporal change in the loss structure of stem rust over time. So for the first half of the 20th century, despite the year-to-year variation, on average there was about a 2.5% loss attributed to this disease. Post-1960, that loss had dropped to just around 0.3%. So again, space and time matter, and you have to take those into account when you do these evaluations. So the work we published last year basically said in the post-1960 period in the US, we seem to have developed management strategies, either genetics or fungicides and so forth, that ameliorated the consequences of this disease in the US. And so we did a counterfactual exercise and said, what if you took those intervention options away, and the stochastic structure of the losses that we observed in the first half of the 20th century actually occurred in the last half of the 20th century as our sort of counterfactual yield. So the yields we see are subject to fairly small losses because of these intervention strategies, breeding and fungicides and other management tools. What if we took that away? What would the yield losses have been like in the latter part of the 20th century? That's a strategy that we used and preserved, rather than just take averages, we actually did this in a probabilistic fashion and preserved the stochastic nature of these yields when we did these analyses. And that's written up and online, so if folks want to see how we did it, it's available. The problem with stripe rust is it's a much more complicated sort of intertemporal pattern. So here we've got data going back to 1960 for the US in terms of this is built up from state level loss data, but this is the national average losses attributed now to stripe rust for wheat production in the US. And you can see sort of three distinct periods here. There's a period, well in fact there's four, one not shown. Prior to 1960, very little recorded losses attributed to stripe rust. And so it was only after 1960 that we got measurable losses that attributed to this disease showing up in the CDL data. For the first several decades, the loss was just over 0.5% per year, and then from the mid-80s on to 2000, that average loss rate dropped substantially down to 0.15% per year, and has now bounced back up in the post-2000 period, at the very time where you saw in the earlier diagrammatic the big change in the spatial footprint of stripe rust losses. That's when you see the average loss rate drop right up to 1.5%. So what we're doing in our evaluations here is taking account of this sort of changing intertemporal nature of the disease, which is quite different than we had with respect to stem rust, and doing a couple of analyses. One to say, what if our counterfactual was a no-loss scenario as opposed to the losses that we observed? And what if our counterfactual scenario was the low-loss middle period compared to the two periods prior to the mid-80s and post-2000 to come up with a mechanism for coming up with a loss attributable to this particular disease. And so, again, as I say, these are subject to final revision and so forth, so this is our first cut look at these, just to try and get a sense of the order of magnitude of these losses vis-a-vis stem rust. The no-loss counterfactual is up on the top part of the slide here, and you can see, depending on the period that you use for your reference period, you can get quite large differences in the losses that are attributable to this disease. And I should point out what we're doing here is this is not estimates just for the US, this is using the stochastic nature of the structure of losses in the US and applying this globally to the world's entire wheat crop by a process I haven't got time to talk about in my 15 minutes here, or 2 minutes left or whatever Bob's going to give me, but we can talk about over the coffee break or whatever. But we can see we can go from a loss in that sort of Mid-period, where we reported very low losses, we estimate globally that would constitute just over 0.3 million metric tonnes per year globally. But if you look at the post-2000 period, where you've got some measured change in the nature of the losses that's attributed to this disease, you're up to just under 5 million metric tonnes a year. And if you remember, for stem rust, our estimates for that were about 6.5 or so million metric tonnes a year. So you're starting to get up into that order of magnitude for stripe rust relative to the losses we saw for stem rust. If you take a slightly more conservative approach in saying that the counterfactual is not a no-loss period, but a low-loss period, as emblematic of that middle period in the US, you still get, in the post-2000 period, you're still estimating globally about nearly 4.5 million metric tonnes a year, which is not chump change. That comes to about $800 million per year in losses attributable to this disease. To take those losses and think about what the R&D investment implications are, again, this is our current, still beta version estimates of that. We estimate that if you took this pre-1985 period, that is these low loss scenarios, they would suggest you'd invest about $8 million a year, which amounts to about 4 cents per hectare in averting this disease globally. If you looked at this higher loss period, post-2000 period, you're up to just under $30 million a year. And again, this is year in and year out. This is not a one-off investment in stripe rust research. This is in perpetuity investment to forestall the economic consequences of this disease going forward. So the comparative information is about $51 million a year we were suggesting for stem rust. So we're in the order of about half or so of the investment that we suggested for stem rust, we're calling for stripe rust. A couple of slides to say our current final work is to look more closely at the interplay between the spatial location of the losses and the magnitude of the losses. If you look here in this earlier period, pre-2000, you can see that the losses, all of the losses in the US, effectively, are concentrated up in the Pacific Northwest and the California area. That's the red bars. There were virtually no losses, even in this post-1960 period, reported elsewhere in the US. If you look post-2000, very different spatial structure to the losses going on. And we're in the middle of disentangling this somewhat complex interplay between location and loss level. So you can read the bullets for yourself, and I'll leave the presentation there. Thanks a lot, Bob.